Hi, my name is Jonathan, and I'm happy to welcome you to my OOPSLA talk on effects as capabilities, effect handlers, and lightweight effect polymorphism. In this talk, I present our language Effect. You can find our language online. The website features an interactive editor and a REPL, so I invite you to experiment with the language. The website also links to our extended technical report containing the full formalization and additional details on our proofs. But before we're getting started, I want to acknowledge my collaborators Philipp Schuster and Klaus Ostermann that contributed to the design of the language. This talk, like our language, is about three things: effect handlers, a recent mechanism to structure complex control flow patterns; effect safety, that is, guaranteeing that all effects are eventually handled; and effect polymorphism, that is, describing programs which are polymorphic in the used effects. While handlers and effect safety are really important, if this talk is about anything, then effect polymorphism. But what is effect polymorphism? Let us consider this example from Dan Lyon's paper on COCA that illustrates parametric effect polymorphism. The catch function is polymorphic in both the value type A and the effect row E. It expects two argument functions, an action and a handler, and uses the handler to remove the exception effect from action. Both action and handler can have additional effects E. We call this form of effect polymorphism parametric effect polymorphism, since catch is parametric in E. Parametric effect polymorphism means that we explicitly bind and reference effect variables, E in this case. Effect polymorphism is great since it allows us to use the catch function with many different argument functions for action, using potentially different effects. Parametric effect polymorphism is common practice in popular research languages like COCA, Frank, or Helium. However, from a practical point of view, parametric effect polymorphism can quickly become verbose and complicated. Programmers are then confronted with type errors like this, or this. While these example error messages are taken from the COCA language, the problem is not specific to COCA, which is a great language. We, that is the Effect Language Research team, agree with Roman Elizarov, one of the Kotlin developers, that working programmers should not be confronted with parametric effect polymorphism. And we are in good company with that opinion. Multiple researchers and language designers have stated that surfacing effect polymorphism should be avoided. For example, Lindley states that in designing Frank, we have sought to maintain the benefits of effect polymorphism whilst avoiding the need to write effect variables in source code. And similarly, Lyon states that in practice, though, we wish to simplify the types more and leave out obvious polymorphism. And these languages go to great length to hide parametric effect polymorphism from the user. However, we believe that hiding the complexity is not enough, since it might still surface in error messages or more advanced use cases, potentially confusing the startled user even more. These concerns are a major motivation of the effect language, which explores a different design space with different trade-offs. The effect system is designed to cater to everyday programmers. In particular, in the effect language, there simply is no support for parametric effect polymorphism. Also, neither source type system nor core type system feature parametric effect polymorphism. It truly does not exist. Since it does not exist, users cannot and do not have to write effect variables, and users cannot be confused by type errors that mention effect variables. Here is the same example in the effect language. Effect introduces a different form of effect polymorphism, which we call contextual. I will go into the details later. For now, it suffices to see that there are no effect variables in the signature. After this talk, I hope that we synchronized on our understanding of effect polymorphism and that you have a good idea of how the effect language enables effect polymorphism without effect variables. I hope that in the discussion following the presentation, we can clarify technical details, talk about implications, limitations, and ways to mitigate those limitations. The core observation underlying contextual effect polymorphism is the following. If a function cannot leave the dynamic scope it is defined in, we do not need to track its effects. Everything in the effect language is built around this observation. While this might be obvious to some of you, let me illustrate this observation with an example. Let us assume the following piece of code. Here, the function definition f uses a get effect with the following signature. We enclose f in a handler for the get effect, which handles get by always resuming with 42. So this example will yield 84. If we know that f cannot leave the dynamic scope of its enclosing handler, then it is safe to not track effects on f. In particular, we can annotate the local function f with an empty effect set. Again, this is only safe if we can guarantee that f cannot leave the scope it is defined in. In many languages, there would be multiple ways for f to leave its scope: by simply returning it, by writing it to a mutable variable, or by closing over it. So, how do we prevent f from leaving the scope it is defined in? Leo Oswald et al. Introduced a type system that distinguishes between first-class values and second-class values. First-class values can be returned and stored, but cannot close over second-class values. In contrast, second-class values cannot be returned and stored, but they can close over other second-class values. In the effect language, we make a similar distinction. It is actually very easy. We treat all data as first class. That includes built-in types like int or bool, but also user-defined algebraic data types. In our type system, we speak of value types. In contrast, all blocks are second class. This includes function definition, function arguments, resumptions, and capabilities. To avoid confusion, we typically do not speak of functions, but of blocks. Similarly, in our type system, we speak of block types. We will see what that means in a second, but let me point out that this implies that in effect, there simply are no first-class functions. We killed every functional programmer's favorite feature. The distinction between values and blocks also shows up in the syntax of our language, both in abstraction, where we expect value parameters in parentheses and block parameters in braces, and in application, where again, value arguments are passed in parentheses and block arguments are passed in braces. To drive that point home again, blocks in effect are second class. They cannot be returned, stored in mutable variables, passed to constructors, and they can also not be passed as arguments to effect operations. So, since a block cannot leave the dynamic scope it is defined in, we do not need to track its effect. However, it is sometimes desirable, as I will illustrate now. By annotating the effects on a block, the user can choose whether an effect should be handled at the call side of the block, or whether it should be handled at the definition side of the block. The different annotations not only affect typing, but also operational semantics, as we will see. But first, let us review our typing judgment for blocks. We can see exactly this. Some effects, epsilon0, are annotated on the function f and need to be handled at the call side of f. All other effects, epsilon0 prime, without epsilon0, have to be handled at the definition side. I want to highlight one important point. Like other recent approaches to effect handlers by Zhang and Myers, or Bernatsky and colleagues, in the effect language we establish some form of lexical scoping of effect handlers. To understand this, let us assume the following higher order function. It takes a block prog and handles get by always resuming with 1. So this example will return 1. Similarly, running f under always 1 will yield 2. However, if we not change the annotated type of f to not mention get anymore, the get effect has to be handled at f's definition side, and now the example yields 84. Similarly, if we change the annotated type of always 1 to not mention get, the handler in its implementation does not handle anything, and our example prints 84 regardless of the effect annotation on f. Our design decisions result in a different reading of type signatures. Traditionally, one would read the above signature as, given a value of type A, the function produces a value of type B and potentially uses effect E. While in the effect language, we read it as, given a value of type A, the function produces a value of type B and requires the calling context to handle effect E. This different reading also has an effect on the notion of purity. While in traditional effect systems one would understand f to be a pure function, in the effect language, f simply admits no direct observation of effects to its caller, but can use arbitrary effects that are handled at its definition side. Only in the special case of top-level functions we can conclude that a function with an empty effect set is actually pure. Viewers familiar with exceptions in Java or effects in multicore or CAML might be surprised to see that our examples have the described operational semantics. In particular, this example yields 42, even though dynamically ignore installs a handler for get that will resume with 1. Our operational semantics is designed in concert with the static semantics such that it truthfully fulfills what the types promise. The type of ignore promises that it cannot observe, that is, handle effects of prog. To obtain the correct operational semantics, we again follow the idea of lexical scoping and translate effect programs to capability parsing style. In particular, for every effect in the set of effects f1 to fn, we introduce an additional term-level argument. If we translate our program using ignore, we obtain the following code. The block passed to ignore lexically closes over the get capability introduced by the surrounding handler. In contrast, if we translate our program using always 1, we introduce another binding occurrence of the capability get, which shadows the outer 1. Our runtime follows a generative semantics and thus prevents accidental capture. Related to the topic of effect polymorphism is another important topic, effect encapsulation. To discuss effect encapsulation, let us assume another effect called abort. We also define a handler, maybe, that handles abort into an optional value. In the following, we adapt an example from the JFP paper Doobie-Doobie-Doo by Convent et al., but first we need some more prerequisites. We define a handler feed that handles our get effect by reading values from a given list. In case there are no more elements, we use the abort effect. We can now compose the two handlers to obtain a new handler called feed maybe that uses the maybe handler to handle the abort effect used by feed. Now, let us assume the following user code. In the function user, we call feed maybe with the block that performs the abort effect. What is the expected result of running this example? There are multiple possible outcomes. First, in languages like multicore or CAML, the abort effect would be handled by the maybe handler and the result would yield maybe. In languages like Coca or Frank, the composed feed maybe handler would simply not type check. The inferred effect in Coca would mention the abort effect on proc since it is used under a maybe handler. This correctly reflects the operational semantics of dynamic handler search, but leaks information into the type signature of feed maybe. It breaks effect encapsulation. In order to restore effect encapsulation, languages like Coca and Frank offer some form of term-level lifting annotation. In these languages, the lifting annotation indicates that any abort effect in proc should be lifted over the next handler, that is maybe. As a result, the signature of proc no longer mentions abort. Lifting has operational content since when dynamically searching for the correct abort handler, lift informs the runtime that the next handler should be skipped. In the effect language, the above example just type checks as is. The mandatory effect signature on proc informs the operational semantics to only bind the capability for get, but not for abort. The user code correctly closes over the abort capability and the program prints aborted. To summarize, the combination of type-directed semantics and the translation to capability parsing style allows us to not require any term-level lifting annotations. The semantics just fulfills what the types promise. I hope that I convinced you that effect offers an interesting lightweight form of effect polymorphism. Parametric effect polymorphism simply does not exist in the language. We also have seen that effect annotations influence the operational semantics. In particular, other than in languages like Frank, it is not necessary to adapt computation using term-level lifts. This simplicity comes with some trade-offs. At the moment, we do not support first-class functions. Also, reasoning about purity is restricted. An empty effect set does not imply that a function is pure. It just implies that we, as the caller, cannot handle any effects. As already mentioned in the beginning of this talk, I invite you to visit our website and experiment with our language.